colors in the microphone there. Elevated from it, so.
Great, thanks, Emily. So I'm going to turn our focus to summertime heat in SPHERE. So I acknowledge my collaborators. Also, this broader NOAA team that's been focused on developing a prototype for the rapid attribution of extreme events, and this is born out of that effort. So we had record southern U.S. heat, the summers of 2022 and 2023, particularly around Texas, early summer 2022. And then 2023, southern Texas extending into Louisiana, also to New Mexico and Florida. So we had all the typical impacts of the extreme heat, records for energy demand, livestock and crops negatively impacted by drought, low river flows, record-setting fire weather, and heat-related deaths. So the questions I'm trying to address here are these three questions. So how predictable were the recent seasonal U.S. heat extremes? What role did anthropogenic forcing play in seasonal heat anomalies? And were there other factors that could have given us advanced warning of the elevated extreme heat probabilities? And just for reference, these are the NOAA CPC temperature outlooks that were issued right before the extreme heat of 2022 and 2023. So I'm analyzing seasonal predictions with SPHERE, and thankfully Andrew already introduced SPHERE, so I don't have to go into this much detail, just noting that I'm using both the retrospective and the real-time forecast for this analysis. And this, we've had evidence that SPHERE has been successful in predicting extreme summer heat. So this is a study by Li Wei Jia in 2022, highlighted in Nature a couple of years ago, showing the potential to predict extreme heat for up to 9 months in advance. So for this study, summer heat extremes were defined as the daily Tmax exceeding the 90th percentile of the climatological distribution. And this map over here shows the skill of the JJA temperature extremes at a lead of 9 months. So you can see significant skill over large portions of the central U.S. And Li Wei recently did an extended study to the skillful prediction of compound humid heat extremes over the southeastern U.S. So that combination of heat and humidity, which is of course very important for human health. Here I'm focusing on the seasonal mean temperatures, and so the bottom line up front here is we see evidence of seasonal predictability for these recent patterns of extreme heat, but we get better patterns after we correct for these trend errors. So for particularly for 2022, this kind of pattern of elevated heat over the south central U.S. we saw even 9 months in advance in our forecasts. And the pattern was pretty much captured about 2 to 4 months in advance for 2023. So here on the top, I'm showing the JJA 2022 and 2023 temperature anomaly patterns. And at the bottom, these are corrected SPHERE forecasts. I'll talk about the corrections here a little bit later, but this is for a lead of 2 months. 1st of April, you can see it showed the real positive anomalies over the south central U.S. where we had the extreme heat. And then for 2023, you can see it did get the pattern pretty well with the positive anomalies around southern Texas, and more of a kind of cooler over the western U.S. But without the corrections, particularly correcting for the trend, you can see it doesn't get the pattern so well. So it overdoes it with the heat. You can see the eastern U.S. particularly patterns off as well. So these corrections are kind of important. And even at a lead of 9 months, so this is the same, but now you can see it showed that positive temperature anomaly of south central U.S. And even in 2023, there's some elements of this kind of horseshoe pattern. So you can get, had some similarity to what actually occurred. So one question, for our source of predictability, is it just the trend? What was the role of anthropogenic forcing in these forecasts of extreme heat? And we can diagnose this with our uninitialized 30-member SPHERE large ensemble that has the historical rate of forcing, but it lacks the initial condition information. So what this map shows is this is basically what our forecasts for these summers would look like if we didn't have the initialization, but we just had our rate of forcing. And you can see positive temperature anomalies everywhere, but particularly pronounced over the western U.S. And so if we look at, for example, this is for last summer, the 1st of April, so lead of 2 month forecast on the top left, and then the right, this is what the forecast would be from our SPHERE large ensemble initialized. And then we take the difference, the left minus the right, you can see this gives us an indication of what role the initial conditions, the initial sea surface temperature, the land conditions, or some combination. You can see you still have these positive anomalies over South Central Texas, cool over the west. So it suggests that a good portion of this pattern, not related to anthropogenic forcing, but also connected with the initial conditions. However, as we mentioned, the trend of the summertime heat extremes is too strong in SPEAR. And so this has been a kind of it seems like an emerging theme in this workshop about these trend errors that are impacting our seasonal forecasts. And this seems to be connected with this so-called central U.S. warming hole, which is really pronounced in the Tmax over the U.S. You can see this is from Aisha et al. In 2020, I think it's 2023, showing the changes in Tmax. You can see in observations of the central eastern U.S. really hasn't been any notable change over more than 50 years. But of course, in our couple climate models, we do see this positive change, and so this appears to be related to both changes in trends in the precipitation, positive trends that are not captured in the model. So there's a component that may be internal variability, but also apparently a component that may be tied to the patterns of sea surface temperature warming and maybe too strong of a warming over the ocean. So I refer you to this paper for more discussion of this. So what I did is just did a kind of a fairly simple correction of the trend, where I just regressed the observed summertime temperature on this rated component from SPEAR. So this illustrated with this Western North American grid point. Here we show in the black is the observed temperature at this grid point for JJA. The solid red line is the time series from the SPEAR large ensemble, the uninitialized, so just rate of forcing. And then the dashed line is just regressing observations onto the SPEAR large ensemble. So you can see it kind of reduces this rate of force component of the time series. So that's one grid point. So this is over the entire U.S. region. You can see after doing this correction, it substantially reduces the trend over most of the U.S. And so the corrected forecast is subtracting out the trend from the SPEAR large ensemble and then adding back in this linearly corrected trend. So I'm not saying this is an optimal way to do it. It's kind of ad hoc, but it's just one way to kind of try to account for this overdoing the trend. And so how much skill, in the summertime temperature is related to the trend and how much is unrelated. So if we just did a forecast using the uninitialized SPEAR large ensemble, this would be our correlation skill. You can see it be quite high over the Western U.S. So the trend is really pretty dominant source of skill over this region, but does poorly over the Eastern U.S. But when you remove the influence of the trend, you can see that at a lead of 0, there's still substantial skill over most of the U.S. Even at leads of 1 to 3 months, you still have positive skill over much of North America. Leads of 4 to 6 months, still positive skill. Even 7 to 9 months, still positive skill. So it suggests that there is skill beyond just the trend related to the increasing greenhouse gases. But keep in mind that this signal we see at these longer leads could easily be obscured by these large trend errors that we see. So after we remove the trend, what are the sources of predictability? And so for this, I use the average predictability time analysis. I don't have time to go into the details, but if you want more details, I'm sure Tim Del Sol will be happy to answer your questions. So I'm happy to outsource that job to him. But briefly, I think of it as finding patterns that maximize predictability. So it's kind of similar to EOF analysis, but instead of maximizing variance, we're maximizing predictability that's integrated over all lead times. And this approach has been applied to other summertime heat, other seasonal prediction problems, like the GI et al. Summertime heat study I mentioned earlier. But here I'm applying it to the North American 2-meter temperature predictions after removing the contribution from anomalous radial forcing. So when I do that, I find that there are 4 patterns that show evidence of that can be skillfully predicted. This is the first pattern. You can see a single sign over all of North America, time series, and correlation skill as a function of lead time. It's hard to see on this monitor, but you can see skillfully predicted on all lead times, correlations between about 0.5 and 0.7. You look at the time series, interestingly, you see the strongest amplitude right at the beginning of negative anomaly. I think this is clearly showing the response to the Pinatubo eruption, where we had a strong volcanic eruption leading to widespread cooling over North America, but we still see substantial variability beyond this period, so it's not all just volcanic response. Mode 2 is more centered over the central US and also has skill out to at least 6 months. Mode 3 is more of an east-west dipole and positive skill at least 3 to 4 months. Mode 4 is more of a kind of northwest, south central dipole, marginally skillful, at least for a few months. And just briefly note, Mode 2 seemed to be particularly important for 2022, Mode 4 more for 2023. And so just briefly mention that we can also reconstruct our forecasts, filter out the higher order modes. And so if we just reconstruct the forecast with these 4 skillful modes and discard everything else, this is the original average correlation skill after removing the trend. And the middle is if we just retain the first 4 modes, and then the difference is on the right. You can see actually our forecasts are generally more skillful with just our first by retaining those first 4 modes and discarding everything else. So the other higher order modes are not really helping our forecast at all. So very briefly, I mentioned Mode 2 was important for 2022, and I argue that it seems that La Nina was a contributor to this extreme heat. So this is the 2022 forecast amplitude. And you can see this pattern, even at a 9-month lead, is correlated with positive temperatures over the south central US. Also correlated with this La Nina-like SST pattern that resembled what occurred in 2022. And this is actually consistent with an ENSO blog post I wrote back in 2022 on La Nina's delayed effect on sizzling Texas summer. So this is when La Nina occurred in the previous winter. This is the pattern you get, and it matches. And this was done independently of this, and you can see matches quite well. So I think it's too coincidental to be just to say that La Nina did have some effect, at least in the 2022 event. And then last, 2023 had high amplitude for Mode 4, particularly at leads of 2 months and shorter. And this pattern is correlated with positive temperatures over the Gulf states. And I'm still trying to tease out the physical mechanism of what's going on, but it's also correlated with the SSTs that matched what happened in 2023. You can see this developing El Nino, but also a tripole over the Atlantic and warm Gulf of Mexico SSTs. So hard, still trying to figure out which dominate, which is most important, but also correlated with positive or negative precip over the Gulf states, which matched what occurred in 2023. Okay, so I'm just gonna end here the key takeaways, and I will leave it at that. Thank you.
All right, we got a question over here.
You're looking at heat extremes towards the end of your, presumably is towards the end of your climatological centering record. So if you're really doing well to predict variability, might you want to look at cold extremes at the end of the record and the warm extremes at the start of the record to make sure that you're not getting extra boost from trend that you haven't been able to remove. Does that make sense?
Yeah. So
because if you look at it like subseasonal models, you see that they do great when you take the whole period. They seem to be doing okay, and then you look at the ends, and you're doing great with the warm and great with the cold on that. You get rid of that, and it's more depressing.
yeah. Yeah, I guess yeah, it would be worthwhile take a dive in there too.
All right, Magdalena.
The area that we're working for is it's an area where the models capture a lot of errors on the blank feedbacks. And the fact that you can reproduce better the skill when you have retained only the core modes related to landscape circulation, it suggests to me that it may have to do with land processes. So how does SPR represent the land processes? Does it have a change in land cover or land use or change in vegetation, etc., etc.?
Yeah, how's, you know how the land is, it's, we have prescribed changes, right?
Yeah, vegetation's prescribed. Yeah, there's no dynamical.
Usually there is constant in the models. I mean, we don't
Yeah,
have.
yeah.
Got maybe an answer.
Yeah. Oh, Wayne is here.
Oh, yeah, that's the
Yeah.
person.
Yeah.
I might have to ask that. What's amazing in this model, that to do that thing, but land model is completely different from GFDL system. And has land use scenarios which come actually from the Maryland, and the same reconstructions that you using say. Also, it has dynamic vegetation model, but probably a source of biases because it sort of predicts that sort of literary events and what are the conservation stuff like that. So there is some preliminary work we did to show that you could do better in seasonal cycles than AI, for example, but the override of AI what is it? By generating model response to whatever climate is doing, in some sense, not out of what's with forcing but it had both land use and responsive vegetation and obviously like snow color. There's a lot of room for
Like that. All right. Murakami up next. Oh, we're clapping you on stage.
Okay.
All right.
Hi, I'm Murakami from GFDL also. Thank you for this opportunity. Actually, this is my birthday, so I never forget it. So I will talk about seasonal prediction of tropical cyclones done at GFDL. So here I show the tropical cyclone seasonal prediction project at GFDL. So GFDL has been supporting experts at National Hurricane Center, the Climate Prediction Center, since 2017 for their hurricane season outlook. So what we are doing is just utilize NNME real-time experimental seasonal prediction using SPEAR. Then using the 6-hourly output, we just detect tropical cyclone from the output, then predict tropical cyclone. So this is more purely dynamical prediction we are doing for tropical cyclones. So NHC and CPC utilize our model, also many other systems like ECMWF model, UKMO model, so they are all dynamical. But most of the models they utilize is not purely dynamical for tropical cyclones. What they are doing that because most of the models are not so high enough for the horizontal resolution to resolve tropical cyclone. So what they are doing is just to look at simulated large scale parameter like wind shear and SST, then just to estimate tropical cyclone from this large scale simulated environment. So we call this hybrid approach. So GFDL is a unique or distinctive NOAA institute to provide the dynamical tropical cyclone seasonal prediction. So however, we utilize FLORA, the previous GFDL NMM model, but this FLORA retired around 2021. So we are now using SPEAR. So it is not documented how much SPEAR has some prediction skill for tropical cyclones. So this is the main goal for this presentation. So quickly, so Andrew already introduced the SPEAR. So I don't go much detail, but mostly that previous prediction system we utilize FLORA. This is a 50 kilometer atmosphere and land surface component coupled with 100 kilometer ocean and sea component. So we had ECDA for ocean initial condition for FLORA previously, but atmosphere was not initialized. So the prediction skill is mostly coming from ocean initialization, the previous system. And Flora, we utilize the 50-kilometer mesh atmosphere, so it's not high enough to simulate intense tropical cycle like major hurricane. So to complement this model bias, so we utilize HiFLOR. Like this is, we just simply increase horizontal resolution up to 25 kilometer without changing other components. So, but when we update our seasonal forecast to SPEAR, so resolution is actually very similar to Flora, but we don't have a high resolution model for SPEAR at that time. So we take advantage of HiFLOR because HiFLOR shows very good scale for prediction of tropical cyclone. So we utilize HiFLOR in the new prediction system, but we don't have ocean initial conditions. So what we are doing is just to prescribe SST from simulated SPEAR SST. This is more like any type simulation we are doing using HiFLOR, the new prediction system. So the motivation for this presentation is just showing that compare the scale of tropical cyclone compare between the new prediction system and previous prediction system. So our target is tropical cyclone prediction for the July to November. So July is the lead month of predictions. And so we have another initial 8-month prediction from like January. So it's like lead month 6. So we have 30-year retrospective season forecast data between Flora, previous prediction system and the new prediction system. So we can compare each other. So we have 15 ensemble members for a new system and 12 ensemble members for previous prediction system. So we evaluate a lot of the tropical cyclone variables, but now we are looking at basin total tropical cyclone frequency predicted by new system and previous system as a function of the lead month at x-axis. So y-axis the correlation scale. Then red line indicates new system and the blue line indicates previous system. So the icon indicates how much the new system is relative to previous prediction system, but just by my subjective feeling. So for the named storm, hurricane, major hurricane, and North Atlantic shown on the left column. So actually we don't see much improvement, but very similar comparable prediction scale for the new system compared to previous system. Western North Pacific also very similar, but we found significant improvement for hurricane prediction by the new system. Unfortunately, Eastern Pacific, the new system a little bit degraded compared to the previous prediction system, especially for named storm prediction. So this is a basin total frequency. So we also evaluate other TC metrics other than basin total TC frequency, like accumulated cyclone frequency, power dissipation index, and also US landfalling storms and Caribbean landfall storm and Hawaiian landfall storms. So what I'm showing here in this diagram, so this is like correlation between model and observation in both axes, but x-axis a correlation between previous system and observation, but that's y-axis the new system correlation between new system and observation. So the different symbol indicate different TC metrics, different color indicate different lead month forecast. So when the plot is over the yellow domain, so it indicates high a new prediction system outperform the previous system. So when you look at the North Atlantic, most of the plot are like over the diagonal line, but when you look more detailed, most of the plots are located in the white region, so that previous system outperform the new system. About 35.7% of plots are located over yellow line. So most of that variable are not so good for new system. But on the other hand, Western North Pacific, we see a lot of improvement for various tropical cyclone variable for many advanced prediction. But Eastern Pacific, so most of the variable are located over the white region. So new system is not good for this Eastern Pacific prediction. But then another open question, why these two model systems show different prediction scale for tropical cyclones? So first assumption is that maybe prediction scale for large scale environment like vertical wind shear may be different. So we look at same plot, but just evaluate the large scale parameter like vertical wind shear, relative humidity, vorticity, and some thermodynamical factor like maximum potential intensity precipitation. But we found North Atlantic, most of the variable new system outperform. So it's very different from the TC prediction where we saw degraded tropical scale. Also, this is applied to the inconsistency also applied to the Western North Pacific, showing not so good for large scale parameter, but actually TC prediction improved in a new system. So this indicates that improved scale in large scale parameter doesn't necessarily lead to improved scale TC prediction. So actually, so we found very interesting season for previous summer season 2023. So what we saw was observation. We saw the very strong El Nino development. When we know that empirically, when El Nino develops, so tropical cyclone over North Atlantic become very inactive because of increasing the wind shear. So, but on the other hand, we also saw the very warm SST condition in the tropical Atlantic. So this may lead more active tropical cyclone season. So these two conditions very contradict each other. So it can lead both either active season or inactive season. So actually, SPEAR predicted very well for this observed SST anomaly, even for the little monthly April prediction. But actually, both SPEAR and HiFLOR is actually share the same SST, but they predict very different tropical cyclone season given this SST condition. Actually, what happened, the blue shows the SPEAR model showing very not so active season, so more like neutral tropical cyclone season, but HiFLOR actually shows very active season. Then open question, why these two models show different TC prediction, even though they share the same SST condition? So what we did is I realized pacemaker experiment. So what I did is just give the simulated SST anomaly by SPEAR, then we forecast SPEAR using SPEAR and the HiFLOR using this SST at a lower boundary condition. So what we found is SPEAR doesn't show much active season for this North Atlantic as we see the real-time prediction, but HiFLOR-S predict very active season. So what I did next is removing SST anomaly over the tropical Pacific. So if El Nino condition suppress tropical cyclone in North Atlantic, removing El Nino condition may lead to more active tropical cyclone in North Atlantic. Indeed, so this SST condition lead to more active tropical cyclone by SPEAR, like 64% increase, but SPEAR HiFLOR actually increased, but not so large. So this means that SPEAR is more sensitive to tropical Pacific SST than HiFLOR. So we did additional experiment removing the SST anomaly over the North Atlantic. It showed decrease in TC by 37% by SPEAR, but HiFLOR shows more decrease, 55%. So this indicates HiFLOR is more sensitive to tropical Atlantic SST. So we also evaluate not only this specific season, but like 20, 30-year retrospective seasonal forecast. So this diagram shows that correlation between TC variable and predicted linear 3.4 SST, and the y-axis TC variable versus tropical Atlantic SST anomaly. So when plots are located yellow domain, so it indicates TC variable are more sensitive to tropical Atlantic SST, whereas when plots are located over the white domain, TC variable are more sensitive to linear 3.4 SST. So left shows the observation. So it shows that except for the US land, for instance, most of the variable located here, like 0.4 correlation between this variable and the MDR SST, but 0.45 correlation for linear 3.4 SST. So it's more comparable SST the sensitivity. But when you look at the different models, so it's actually HiFLOR shows similar observation. But when you look at SPEAR, it's very different from the lead time prediction. Longer lead time prediction show more sensitive to the linear 3.4 SST, but when lead time becomes shorter, so it become more like observation. So it's largely reflecting the 2023 prediction where long lead month prediction show neutral, but shorter lead month shows the active topical cyclone by SPEAR. Okay, so this is the takeaway. So new GFDL TC S2D prediction system demonstrates skillful prediction of TC activity across the 3 ocean basins. So what I'm highlighting here, the different scaling TC prediction is very complicated, and they are not so relevant to the changing scaling large scale environment. But this study highlights the importance of the not only improving the prediction skill of SSTs and large scale environment themselves, but also enhancing the model's response to of the TC to such large scale condition like SST and large wind shear may lead achieve further improvement in TC prediction. So that's all my perspective.
All right, anybody got a quick question? Christina.
So, I know that the relationship between the El Nino and the tropical cyclone in the Atlantic happens to be wind shear in the MDR region, and models have different relationship between El Nino and the wind shear over the MDR region. Have you looked at that? To see they tend to have different wind shear?
Yeah, I have not much analyzed that, but I know that what you mentioned, model responds differently for wind shear to the El Nino condition. But observation, I know that mostly wind shear affect the Gulf Mexico region, not the MDR region. So the El Nino partially impact North Atlantic tropical cyclone, but not homogeneously. So another factor may also like Atlantic meridional mode may also impact the tropical cyclone genesis over North Atlantic. Yeah.
Thank you.
Thank you. All right, thank you. We'll go to CPC talks, Bohar Singh.
Thank you for joining us. From the previous talks and from yesterday's, we have seen that the model has systematic bias. So it's a standard practice to correct them before we use any decision making. So traditionally, we are using the linear methods to correct those bias. But recently, use of artificial intelligence and machine learning in our field is gaining popularity. And there are some methods used for post-processing in seasonal and subseasonal forecast. So, due to because machine learning methods are data hungry, data intensive, so we have to. There's a question if we have enough data to so that the machine learning can learn something more than the linear methods. So that is the goal of this talk. So we have used the NMNE data and including ECMWF model. There's a typo. We are not using GFDL SPEAR because of the hindcast coverage. We are using models that have a hindcast coverage from 1918 to 2016. We have 35 models. We have use the 2 regions where the international desk work as a 2 forecast, West Africa and region for Central America and North South America and Caribbean. For the West Africa, we choose the June to September season. For Central America and North and South America, we use August to October. And the forecast initialized for the West Africa is June 1st and July 1st for our region. And we have tried various predictor domain that is for CCA. And for the reference, we have used the CHIP data, and we use a multi-model ensemble from all these models. And for validation, we have used 5-out cross validation. So this is a one glimpse of how the climate bias look like in seasonal climate forecast. Top one is the raw MME. Raw means without bias correction, and other is observation from CHIP. We can see that model is able to simulate those. So model is able to simulate those maxima in precipitation at the right place, but their magnitude is lesser in the simulation. And if you look into the time, you can see that notice two things from this time series, which is red observation and blue is raw. So first is the model consistently overestimating the precipitation at that particular grid point in magenta color. And then second is that they'll be artificially suppressing the variability of those variation, year-to-year variation when we are doing the multimodal concepts. So we have used three methods for comparison: CCA as a baseline method, and then ELR, which linear, which learn decision boundary linearly, and then the newly developed method by Nathiketa, which is called probabilistic output of extreme learning machine. And he has extended this method to give the full PDF. And luckily, he has coded those methods, all of them in a one Python library, which is called XCast. And we have used XCast in this analysis. And so the verification methods, we focus on accuracy. So for the deterministic bias corrected hindcast is judged by Pearson correlation and root mean square error. For other two methods, ELR and EPO-ELM provide probabilistic output for three categories, below normal and above. So we use our rank probabilities score, which is measure the squared error in probabilities. And then RPSS is basically the comparing the forecast with the baseline. So for here, we have a baseline, not a climatology, the CCA. And then the reliability scale to assess how good your calibration works. This one, so nice. This one?
Yeah, that's pleasant. Yeah.
Okay, for CCA, we have used a predictor and predictor modes and 6 CCA modes, and that's a predictor and predictor domain. For EQLM, we have tried various activation function, but we have chosen the linear and nodes 10 node. We also tried 5 node and random initialization 30. And this is the bias correction from CCA. You can see that the bias can be corrected for the magnitude for those precipitation maximas, and also corrected for the mean and those amplitude bias for that particular grid. That's how the CCA works at all grid points. And this, but you can see that the bias is removed greatly, but there are some due process of generalization. We will bring some new biases in some regions, but some biases still remain. And though the CCA gave us bias corrected hindcast, which is deterministic, so we have to convert into probabilistic by using the mean prediction as a mean, and the error we make over the hindcast period as a spread. So this will be the comparison. For the next, we are comparing those three methods in terms of how much error they are making on their probabilistic forecast, the RPS score. we can see that the CCA and ELR are making the similar type of similar magnitude RPS error for both of the regions, but ELM's EPU ELM's RPS error is slightly high over both of the regions as compared to others. And though there are some regional differences, and when we are looking at the significance, how many times those forecast better, so that if we can see the difference between ELR and CCA, EPULM and CCA for both of the regions. And wherever the red in color, this means CCA is doing better as compared to other modules, whereas the blue in colors, then the ELR or EPULM is doing better. So then we, for the significance of those, we judge with how good those are going on. For each forecast, we use the sign test for each time samples. So then we check which forecast wins, and we count the number of wins and loses by 1 and -1, and that follow the binomial distribution. So by judging this significance level, if your p-value is below that, then you're significantly different. We can see that some regions, in the blue region, specifically in the first column, the ELR is winning some points, wherever the CCA is better on some regions in northern South America, and EPULM is performing better in parts northern Africa, but our other regions, CCA is performing better as compared to EPULM. And similarly, that this RPS score looking at other ways. So as compared to CCA, wherever the color blue, the CCA performing better, and wherever the color red, the other competing model is competing algorithm is performing better. So most of the places, CCA performing better than EPULM, and ELR and CCA is performing competitively. So this is the reliability diagram, which have a lot of detail on it. So it tells about that resolution, about reliability, and the sharpness about the forecast. So you can see that ELR forecasts are well calibrated, though they are less sharp, because those probability they forecast is always between 0.2 and 0.5, and the CCA is a little bit better than the ELR, but their reliability is less than as compared to ELR. However, EPULM is outside of this area, and those forecasts are not reliable. Most of the time, they are sharp but not reliable, and their resolution is also less. So that's my takeaway, that ELR often provide correct result but tend to lack in confidence for the prediction. In contrast, EPULM give stronger probabilities, near 7, but then when it's incorrect, it's heavily penalized. And over 35 of time tasks, ELR perform comparably as CCA, and EPULM perform less effectively than CCA. It's not the question that EPULM is not able to learn, but we have a limited hindcast. With the 35 samples, we are expecting a lot from machine learning. So for this number of samples, we should compare with our linear methods and take the system. I'm happy to take questions.
Questions? Yes.
Yeah, I'm curious if the ML bias correction techniques you're looking into, if they can also shed light on avenues for model developments and help understand where the biases may be different.
In the bias correction?
Yeah, can the bias correction technique be further analyzed to potentially provide avenues of?
Okay. I think we'll move on. Thank you very much. Our last speaker, Dan Collins. Thank you, Dan, for closing that door.
Yeah, just push forward.
Yeah, or there's the.
Oh,
picture also
yeah.
works, yeah.
Okay. Shoot that slide right there. Up forward.
Oh, is that that?
Yeah, going back. Yeah. There you go. Yeah, good. There you go.
Okay.
Okay. So, I will be speaking about the seasonal climate forecasts, at CPC, Climate Prediction Center. So this is a theme that we've seen, a number of talks hit on, the non-stationary climate, or the trends in the seasonal forecasts and in the models. But from a perspective of making the forecasts, I'm going to be presenting today, and there you can see those who contributed to this discussion of forecasting with trends and non-stationary climate. So just a little bit of background, not mentioned here. I'm going to be using the NMME, North American Multi-Model Ensemble models for this analysis. So as we know, climate change is a increasing impact on S2S forecasting. You can look at this in terms of the last 10 years or a recent period, and the upper tercile, the upper third of the climatology is being forecasted much more often than it was prior. I will show that this can be more than 50 or 60% of the time. Of course, anywhere that trends are positive, we would expect more above normal forecasts than below normal forecasts. So there's no way of getting around this if we use the 30-year fixed climatology, which is the WMO standard. For simplicity, I'm showing some corrections using a simple linear regression methodology. There are obviously other ways to calibrate and correct your forecasts. Looking at a deterministic skill with correlation, and looking at probabilistic skill with the HiFLOR skill score, which is just a % increase in hit rate for each category. So as noted, above normal temperatures relative to a 30-year climatology are increasing in frequency over time. So here we take a look at that. The first row shows the 4 seasons from 1991 to 2005 relative to the 1991 to 2020 climatology. I know you can't read the actual key, but the blue colors begin with less than 30% coverage of above normal in the observations. So you can see many areas where it's less than 30, the darker blues are less than 20, and there are even areas where it's less than 10% in that early first half of the climatological period. It's not the same for all seasons. If you look there at the winter season, which is DJF on the right, you can see actually in the early part of the climatological period that there was more above normal in the central parts of the United States, which is somewhat different than the other seasons. Also, if you look at the last 15 years, that's the middle row. Of course, you see more red tones. The pink and red begins at greater than 40% or 50% in that last 15 years. And if you go to the most recent 10 years, then you see those areas become more pronounced. Some areas, as noted, exceeding 50 or 60% of the time for above normal. And this is even shown to be even more significant in the most recent years, and it would be in the real-time forecast as well. The third panel there is the last 5 years of the climatological period. You can see there's areas in the west and areas in the northeast where it's actually 5 out of 5 years were above normal. So if we look at the dynamical models, it's been shown repeatedly. Those forecasts even more often above normal than the observations. The observations are the black circles. So you see the different years across the climatological period. Then you see the 10-year averages, the first 10 years, last 10 years. You see how there's been more above normal. The red lines show the averages for the models. The dotted lines don't show up very well. Those are uncalibrated. But calibration, what I want to note in this is that calibration through this simple linear regression methodology. So that accounts for the skill, the correlation skill of the forecast.
that damps the signals, that damps what's the anomaly shown in the forecast according to the signal. And with that reduced signal, it's even less likely that you forecast below normal. So you're forecasting above normal even more often when you account for the scale of the model. And then the solid lines are actually a trend correction forecast. As you've seen, others have done trend corrections. This is that simple trend correction. And the trend correction suggests that you would even forecast above normal even more often. So here's just reinforcing that the decadal trends in the models are different than the decadal trends in the observations that you see on the right. So you see in all the models, there are trends that do not appear to be to match the observations in various seasons, various regions. So these, as noted previously, these trends show up very early in the model forecast. So you can look at the 0 lead 1 month forecast and then assemble that into winter seasons and other seasons. And again, you see that the model forecasts, even in the first month, that the trends do not match the observations. So what can we do? One possibility is to look at an alternative climatology instead of going with this fixed 30-year climatological period that we generally have done. And you can see how much of an impact that has on the coverage of above normal in the forecast. You could look at these relative to a sliding climatology. There you see a figure from Risby et al. 2021, which suggests various ways in which one would train bias correction and look at forecasts in terms of climatology. And so we're using a 10-year and a 15-year sliding climatology. This is equivalent to what we call it the Climate Prediction Center, the optimum climate normal, work by Ben and Bill some years ago, showing that this is a period which would predict the trends going forward. So if you look at the skill in terms of correlation of, in this case, it's the CFS V2 forecast with this fair sliding 10-year climatology, and compare that to the 30-year climatology. On the top, you see the 30-year climatology correlation skill for the 4 seasons. And you can see there's areas where you're lacking skill, but generally you have positive skill across much of the map. The green tones for reference are greater than 30% correlation. The 10-year climatology, sliding climatology is in the middle. For some seasons, you can see actually have a gaining skill, which might be surprising, but of course we're removing prediction of the trend essentially. We're predicting relative to the trend. So the models do have skill in forecasting variability relative to the trend as determined by a 10-year sliding window. At the bottom, you see the difference. You see in some seasons, such as in the spring season on the left and the winter season on the right, you largely have gains in skill by looking at it relative to a 10-year climatology. In the middle, it's a bit more mixed for the summer and for the autumn seasons. But generally, skill is comparable and is largely positive. That's the main. This is also true for various models. So this slide I'll just move through quickly, but you can look across the different models of the North American multimodal ensemble and most models and see similar picture in terms of how the skill compares to a sliding climatology relative to a 30-year fixed climatology. This is also just comparing models a different season. And again, you see a similar picture. So we may want to look at different climatological periods. 15-year climatological period would have a smoother transition from year to year. Obviously, if you're doing a sliding climatology, then you're always changing what your reference is. But if you look at a 15-year sliding climatology, you don't actually largely see that much difference from the 10-year climatology. You do see a little bit of damping relative to the 30-year fixed climatology. So those differences, that's what I'm showing here. The difference for the 15-year relative to the 30-year climatologies is the patterns are very similar to the differences for the 10-year climatology. However, you see a bit more muted differences. So somewhat similar. So you're not removing the trend as fully if you're using something like a 15-year climatology. And so you end up with forecasts that are similar for better or worse, that are similar to the 30-year climatology. So forecasts using a varying climatology are skillful, but alternatively, we could try to correct the trends in the model forecasts, as already noted. But that would mean, of course, that the forecast still would largely be above normal. So in terms of calibration and correction of the models, we use in this simple linear regression. And then that second equation shows the addition of another term, capital T, that's for trends. But primarily, I want to focus on the optimum climate normal as a predictor of trends. So now we use a multivariate regression for the model forecasts plus a predictor for the trends using the optimum climate normal. So the light blue, they're circled in the upper left for winter. You can see that that has comparable skill or better. That is when we use the trend predictor or the using the OCN last 10 years as a predictor of the current season, that we generally improve the skill or have comparable skill to using the model forecast directly without a correction of the trend. In some seasons, the trend's very strong. That's the autumn season in the lower right. And there we don't really get much in the way of any kind of gain from including an OCN predictor, but a linear trend, which, you know, may, for better or worse, would better predict the trend in that case. So here's my summary. So the coverage of above normal relative to the 30-year fixed climatology is increasing. Real-time forecasts following the climatological period here would have even more above normal temperatures, given the lag between real-time forecasts and the 30-year fixed climatology. The model biases associated with decadal trends appear within the first 30 days of the initialization of the forecasts. So they are errors integral to the models themselves or the initialization. The models have equal or sometimes greater skill in terms of anomaly correlation if you predict relative to a sliding climatology relative to the most recent period, 10 years or 15 years. So we can also alternatively correct the forecasts using a predictor such as the recent 10-year period. If we do that, we can improve upon skill, but we will have more coverage of above normal across the domain. So essentially always predicting above normal and only qualifying the commenters in that above normal forecast. So that's it.
Question for Dan. Gina?
The previous slide, where you show different models, looks like some models are more sensitive to the methods than others. Do you have any insight in that?
Well, for one, the trends are not the same across the models. They actually can be somewhat different. So they're different from observations. They're also different than others. Some models have a very strong trend or have a weaker trend than observations in some cases, in some areas. So those corrections and how well they work to give you any benefit relative to the model is going to be relative to the model trends for sure. Also is going to be dependent on the model skill and predicting other variability, obviously.
Thank you. I know we're going to the coffee break, so I can't ask you after, but just in terms of the sliding scale, like you start using like 10 or 15 year with the sliding climatology. Did that change how we're communicating to decision makers going forward? And what are your thoughts, the implications of that if we're starting to put this into like a heat wave forecast for someone who's trying to do this volunteer weather service?
Yeah, this is something obviously we definitely need to understand if we want to characterize our forecast relative to its sliding climatology. Some users really, the 30-year fixed climatology is not necessarily optimal for how they want to look at the forecasts. Some users really do want to know how does this compare with recent years and for the current climate. Obviously, they'll change. Other users like you said, you have to be careful, communicate well that if we're forecasting below normal more often, that's because it's relative to what we see to be the current climate state, the current 10-year period. So they have to understand that.
All right. Well, let's thank all our speakers. Thank you, everybody. Sorry to talk during the topic of it.
Yeah, right.
Are you sure? No, you're
Yeah.